2 minutes. 2 minutes. Okay, 9:45. Let's get rolling. It's gonna be a light one in person today, huh? That seems like a poor decision, but anyway, we'll keep going. Lord, thank you for bringing us together this morning. Thank you for uh, everything that you do for us. I pray that you would continue to bless us, that you would help us to strive in this semester, that you would help us to get everything done that we need to get done. In your name we pray. Amen. All right. So I want to do some stuff today. What are we going to do today? Right. Well, that's not. My camera probably turned off. That's fine. Play this game all day. Play this game all day. All right. So again, we have what seems to be a laundry list of things to cover today. Right. Not all these are super long. Right. But what we're going to do is we're going to recap last class about block diagrams. Right. So we're going to start off with that. Then we're going to transition into differential equations. Now, you took a whole class about differential equations, so I'm really hoping that this is more of a knocking of rust off than a repeat all of differential equations in the span of a single class, because that's not the intent, right? So if you're feeling like you don't remember a lot of your differential equation stuff that you need for this class, go back, review your notes, come to office hours, and we can talk about it, right? But those are the things. Oh, also for you guys who are in class right now, I learned a thing. Right? If I do this, then the bar goes away from the top of the thing. Hey, look at that. Learned a new trick. Very excited about it. I hope I can get that back though. All right. So, well, it just comes back when people want to get into class, huh? Let's see. I'm gonna go. All right. So, as one way of recapping, right? Models, junctions, block diagrams, and so on. So those all fall into block diagrams. What are we trying to do when we make a block diagram? We are trying to recreate the modeling equation, right? The equations in motion that we created in our model, right? We're trying to get a graphical depiction of those system equations. Right? Eigenstate. We didn't talk about eigenstates. We didn't talk about that. I think we haven't talked about eigenstates, nor will we really talk about eigenstates. We will talk about eigenvalues, so I guess we will kind of talk about it, but that's a much later topic than what we're going to go through today. Right, models. When I say models, I mean our systems of equations, right? Our systems of differential equations that we have, right? The whole focus of the first, 5 weeks of the class where we did nothing but make models, right? If you're still having issues with the modeling process, come to office hours, right? Come to office hours. We'll go over it as much as you want, right? So do that. But a block diagram is just another way of representing these models that we've been producing. A junction is the same as if we were talking about a circuit, right? It's anywhere where we have multiple signals that meet up together. Specifically, a summing junction is where we have a bunch of things that can come together and we're either adding them or subtracting them. Right? Remember, every part of our block diagram represents something mathematical, right? So if we have two things, a wire and a signal coming into a block, that's multiplication. If we have a wire going into a junction, that's subtraction, right? That's addition or subtraction. We are going to do this example though, right now. Let's work on this one. Okay. So in this case, we're not coming up with the model. There's no problem saying, right? So what are we supposed to do? Well, what we want to do here is we want to determine what is our equation for x of t. Essentially, right? What I want to do is I want to collapse this down. And I want to make a system-wide transfer function. Why would I want to do that? I want to know how the input and the output are related to one another. That's what the transfer function tells me, right? It's the ratio of my output to my input. So I want to collapse this entire block diagram down into a single transfer function. Into a single transfer. Okay, so how should we go about doing that, right? Well, I'm going to come here for a second, and I'm going to just make a note on this diagram. Okay. And I'm going to say that we're going to call this signal that's coming out of this node, I'm going to call this D, capital D. Well, no. Let's call this something else. All right. We'll come to that in a second. Right? So let's start. We'll start here, right? We're going to start at our junctions. Well, how do we attack this, right? Remember, we have specific rules that we can follow, right? Like if two things are in series, we can collapse those together, right? Or if we have a feedback loop, a negative feedback loop, we know how to handle that from last class. Or we can brute force these things, right? So what you're going to see right now is I'm just going to take these nodes and I'm going to color code them because I'm going to address what's happening at these nodes first. Okay. So if we look at that first red node there, right, what is this telling me, right? I'm going to interchange f of s with lowercase f of t here because we want to do this in the time domain. And so all of these become lowercase. Right? And you see a capital operator that tends to tell you that we are in the Laplace domain. And so lowercase is the time domain. And so I'm going to refer to these as f of t, w of t, right? So we're looking at this red node, right? This red one. At this red node, what do we have? Well, we have ws coming out, or w of t. Right? So w of t has to equal what? Well, what's entering there? Well, we've got positive f of t, right? minus, how do we know it's minus? Look, there's our negative sign, right? There's our negative sign. So what's coming in there? Well, it's 4 times something, right? Let me run this back. Let me run this back. I hit 4 times, oh, it's x of t. 4 times x of t. Everybody with me so far at that junction? We follow. Maybe. All right. So let's move to the green one, right? So if we move to this green junction here, we move to this green junction. What do I have? Well, this one's a little tricky, right? Why is this one a little tricky? Well, I don't have any fancy signal names coming in or out of that, right? So I've got some signal. Well, hey, take a look at this right here, right? If we're coming in here, well, this is just 7 times W of t, right? Because I have W of S, WT goes into 7, so that's 7 times that, right? Well, that's not an equal, sorry, remember that's going in. Plus, well, plus a negative, what's it subtracting? Well, if we run it back, it's 3 times x of s. So 3 times x of t. Remember, we can interchange those in our analysis right here. But what comes out? There's some signal that comes out there, right? So I'm just going to call it, for right now, C of t. Okay? I'll call it C of t. Remember, in our time domain, right, this 1 over s becomes 1 over d, right? 1 over d. This one also becomes 1 over d. Okay, so let's look at this C of t thing, right? The C of t variable that we just made. If I multiply C of t times 1 over d, I get y of s out. Right? What is the function of that 1 over d block? What is that supposed to do? What type of block is that? Leave back in your notes the last week when we went over the types of blocks. Last class, not even that long ago. 2 days ago. What are the different types of blocks that we have? We've got a summing junction, which we've been using pretty exclusively to this point. We've got
transfer function.
Integral, yes. Right? So 1 over d is an integral. So if you take the integral of something and you get y of t, doesn't that mean that what I had going in was the derivative? Right? So really, instead of calling this, my pen just done. I think my pen just done. Oh, this is going to be lovely. Oh, I'm getting something. There we go. So instead of calling this C of t, couldn't I just call this d the operator for a derivative times y of t, right? This is just dy of t. Okay. So we move to our blue, right? And at the blue, we've got y of t plus g of t is equal to d times x of t for the same reason, right? Because whatever is on this side here, right, that's going to my integral block comes out as x of t, right? So that means I had the derivative of x of t. I had x dot there, right? I had x dot. You can also think of this as being y dot of t, and this is d times x of t, or x dot of t. Is everybody following me so far with what we've done? Everybody okay? Hey, see everybody who's got cameras on their head, something. Tell me something. Are we understanding? You can unmute, you can tell me if you're not understanding. You can tell me if you are.
I know T is relating to time, but why are we switching the S's to T's?
Sorry, say that one more time.
Why are we switching the S's to T's? I know we're relating to time, but
Dante, we haven't done anything in Laplace space yet, and we're going to do this as a time domain transfer function, right? So S is the Laplace domain variable, and T is our time domain variable. So instead of using a Laplace transform, we are going to use a time domain transfer function that has the D operators.
okay. And for the G of T, how would we know if we were making it to make that a plus? Like, why is that also a plus?
Because if you look at the blue summing junction, right, there's positive signs of both the things going in there, right?
Right. How would we know if we're making it to do that?
So how, like, if you had the equation, how would you know? Because
Yeah.
you have y plus g at some point.
Okay.
Right? So remember, this is just telling us at that specific summing junction, I've got y plus g is equal to x dot, right? That's the, so you'll end up with a system of equations that you're trying to put together graphically, right? That's what you end up with.
Okay.
So we can start doing some algebra here. What we want to get at the end of this, right, is x of t over f of t. So we want this transfer function. But actually, right, we've got two things that we want to get. Because I've got two inputs. I've got g of t and I have f of t, right? So I need one transfer function for each. So let's just do the math first, and then we'll come back to that. So we're going to take that third equation, the blue one, right? I'm sorry, the green one. We're going to take the green equation for dy of t, right? dy of t is equal to 7 times w of t, right? So 7 times, I'm going to plug in w of t. Okay. Minus 3x of t. Right, so I've just taken that green equation, right, and I've substituted in the w of t equation, the red equation, right? I think it's pretty clear where I put each of those and when they fit together. So what we're going to want to do is we're going to want to expand this first expression here, right? Because we've got 4x of t times 7, right? So we can, well, I'll just write it underneath. We can rewrite this be 7 times f of t minus 28 x of t minus 3 times x of t. So we get 7 f of t minus 31 x of t. All right. So I have an expression for y of t because I can rewrite this. I can divide out by d, and I'll get 7 over d times f of t minus 1 over D times F of T. Right, just did a little algebra. Remember, you can treat the D as an algebraic variable, right? You can just treat the D like it's a variable there, and I want to get y of t by itself. Right? Why? Because I'm going to plug that into the blue equation. Right? I'm going to plug that in to the blue equation. Is everybody with me so far on this? Yep. Okay. So I'm going to take this green equation, right, this y of t equation, and I'm going to plug it in up here, right? So that's what we'll do on the next slide. All right, so if I rearrange this, well, if I write this as dx of t is equal to g of t plus, well, y of t, we just found out, was 7 over d f of t minus 31 over d x of t. Right? So I'm just taking that equation, and I've got, notice, this is basically everything that I need, right? Right? Why is it everything that we need, right? Because remember what we're trying to make, right? We're trying to make x of t over f of t and x of t over g of t. Yeah, question.
How'd you get 31?
How did I get 39? 7 times 4 is 28. So I got negative 28 minus 3 is negative 31.
Thank you.
Can you explain really quick again why it's x over f and x over g?
Because the transfer function is the ratio of my output to my input. Right? But I have
yeah.
2 inputs. So I need as many transfer functions as I have input-output pairs. That's what we're looking for. We're looking for the transfer function with respect to f as my input and the transfer function with respect to g as my input, right? Let's keep going here, right? So I'm going to multiply through by d here. Right, I'm going to multiply through by d, and I'll get d squared x of t is equal to d g of t plus 7 f of t minus 31 x of t. Okay. Then I'll bring this x of t over to this side, so I'll get d squared plus 31 quantity times x of t is equal to d g of t plus 7 f of t. And we're almost there, right? So how do I isolate these? How do I isolate these things, right? How do I isolate to get just x of t over f of t and x of t over g of t, right? How do I do that? Because right now I know that I can get this transfer function, right, for both inputs together, which would look like this, right? We've done this one before. Right. We've done that. That's for both inputs together, right? When we did our motor, we took TL and the load torque and the motor torque, and we put those together, right? And said that's one input, right? And certainly we could treat it like this, right? But if I wanted the transfer function just due to the effects of f of t, I want to know, how does my output change just because of that input? And how do I do it, right? How do I do it? The standard practice is to set the other inputs to 0. Okay? So you set G of t to 0, right? So I'm going to take this equation here that I'm putting the bullets next to, right? And I'm going to set G of t to 0 in it, right? And if I do that, I get d squared plus 31 times x of t is equal to 7 f of t, right? So my transfer function of x of t over f of t is 7 over d squared plus 31. I can do the same thing where I keep I set f of t equal to 0. Excuse me. And we're left with this. So there's 3 ways that we can report the transfer function here, right, for this particular system. We can report it as a combination of both inputs. We can report it as just a function of f or just a function of g, right? So think about it this way, right? If you have both of those inputs and you want to know how the total system responds to both of those inputs, you need the blue transfer function, right? If you want to know just how your output changes based off a very specific input, well, that x of t over f of t is good for you, right? But what if you wanted to use the other one? Well, that's x of t over g of t. Another thing to notice when you're looking at this is, maybe you did notice it, the total transfer function is just the sum of both of my individual transfer functions, right? If I added both of these responses together, I get d plus 7 over d squared plus 31. That's superposition, right? That's one of the characteristics of a linear system. Okay. So if you want the transfer function due to both inputs, that's fine. You can use the blue one. Or you can break it down to the specific response of other inputs, right? Of just f or just g in this case. How do we do that? We just we set the opposite one equal to 0, and we solve our equation and find the transfer function. You guys have any questions? What if you wanted to draw a new block diagram for this, right? What if you wanted to draw a new block diagram? Okay. Sure. We sure could. Oh, I'm gonna have a slide real quick. Please hold. Let's draw our new block diagram based on our new transfer function. I realize it's frozen. Please hold. The call is important to us. Right, so remember, our transfer function, our overall, let's look at this one. This transfer function, right? That was d plus 7 over d squared plus 31, right? So I can draw a block diagram for this, right? What's happening here? Well, I've got some signal. It's going to come into d plus 7 over d squared plus 31. And we're going to get x of t out. What is this signal? F of t, and g of t, right? What if I wanted to use the other two together, right? Well, you could break this down, right? You could break this down as, if you wanted to use these other two transfer functions. Give me a sec. Okay. I want to use these two, right? I want to express each one individually, right? And we'll start with the f of t one, right? F of t, x of t over f of t is 7 over d squared plus 31, right? So you have f of t times 7 over d squared plus 31. That gives me x of t. And you get g of t. Then what happens? Well, really, what happens? And since these are two parts of the same whole, excuse me, this. You have to add f and g together, right, to get the actual x of t, the total system level. Both of these are equivalent, right? Both of those are equivalent.
Dr. D,
Yeah,
if you cross multiplied the g of t plus f of t to the d plus 7, would that come out with the expression, the dg of t plus 7 f of t?
for this one, right? You get to that, right? Which is exactly what this block diagram here is telling us, right? That's exactly what we're doing, Dante, in a sense, right? Is you're creating this equation for x of t. How do we get there? Remember, the transfer function times my input function is going to give me my output, right? That's the power of the transfer function. I can create this ratio of output to input, and if I multiply that by my input, I will then get my output. And this is going to become really useful for us when we do get to Laplace transform, and how we handle solving differential equations using inverse Laplace transforms instead of doing it the way that we're going to do it today.
All right. Maybe I'm looking at it wrong, but wouldn't that give you a expression, if we were just looking at the top, the d of g of t, which we want, but then wouldn't that d go to the f as well, and then the 7 would go to the g as well?
Yes, right. It would if you're doing it algebraically out like that. But
Oh, so we're kind of just doing it componently, so it's not straight algebra right there.
I mean, that's another way that, remember, there's more than one way to draw these correctly, right? So you could, if you wanted, right, have this be, you know, and have f of t right, and then both of these come into a summing junction as well. And you could have that like that as well. It all depends on what you start with.
Okay, I kind of see how you. Okay, I get it.
It all depends on, like, there's multiple block diagrams, right? So how do I know I did the right one? If you can get the equation back out that you started with, right, then you should be fine. Okay. So remember, if you don't draw them, the way that I was taught is slightly different than what's in your textbook. I was taught that the negatives are really important, and if you ignore the positives, it doesn't make a difference because people will know that that means it's positive. So if you forget one, I'm going to assume that it's positive, right? If you don't include it, I will assume that you meant positive. So if you mean negative, make sure you got negative. It's probably a better practice than NMT to actually notate all of them, and I'm probably doing it wrong, but I've been doing it. When you do something a certain way for a long period of time, it's hard to change. But I'm working on it. Keep calling me out on it. No, seriously. It's better practice. It's a better practice to put your signs up. All right. Any other questions on this?
All of those ways are would be acceptable, like homework. And there's
So
say there's more than one right way to
the
do it.
question is, on a homework or a test, are all of these acceptable? And the answer is that it depends, right? Because we saw in the one that we did in class the other day that it specifically asked you for a specific variable, right? So if you had a block diagram that didn't include said variable, then that would be wrong. But for something like this, find the transfer functions, you probably won't be asked to draw the block diagrams, but just to find the transfer functions, right? In Simulink, right? And this is going to be mostly, you guys, if you've looked at the homework yet, the homework is, there's some stuff that you do by hand, but some stuff that I expect you to use MATLAB and Simulink to do, right? We're going to go over MATLAB and Simulink, right, in a couple of classes, but you're going to start to be able to check your hand responses, right, with MATLAB or Simulink for your model, okay? That's kind of the idea. All right, I was told last time that I didn't change these in all of my classes. They're definitely correct now in MATLAB, so there's that, right? So these are homework 4, lab 2, homework 4 on the 8th, right? Homework 4 is available in the announcements, right? So take a look. You might not be able to do all of it right now, but you can do at least half of all the problems because you are going to have to model some of the systems, right? So take a look. Lab 2 is 11:15. Right, that's going to be online again, just like the Pendulum Lab. In fact, you guys could go and watch Lab 2 right now if you wanted to. Right, it's up there. Dr. D and Professor Price do labs, episode 2. It's a hit YouTube series. We've got literally tens of people who've watched it. It's great. Homework 5 due on the 22nd, and then exam 2, the class before Thanksgiving. Okay. We'll talk more about that as we get there. All right, so let's talk about differential equations. Right, this is like the greatest hits of all the things that all of the engineering students love. Right, we do circuits, we do thermal fluids, and we do differential equations. That's everybody's favorite thing. Right, look under your chair. You get a differential equation. You get a differential equation. Right, everybody does. Great. So suppose I have an nth order ordinary differential equation. We're going to set it up as an input-output equation. Right? So all my inputs are on one side, all my outputs are on the other. It's got one dynamic variable y and one input. Right? So this is a single input, single output system. You can think of it as a mass spring damper if you want. Right? It doesn't really matter what it is. Right? So as an example, we're going to consider a second order input-output equation. Right? second order equation that looks like this. We've got 2y double dot plus 2y, 12y dot plus 16y is equal to 3u of t. Right? 3u of t. From differential equations, I hope that this sounds familiar, but you can create a total solution, which we will call y of t, and that is comprised of two parts. This is the homogeneous and the particular solution, right? So the total solution y of t is equal to the homogeneous solution y sub h of t plus the particular solution y sub p of t, right? So you need both the homogeneous and the particular solution to get the total solution, okay? What is the homogeneous solution? Well, this is the solution to a homogeneous ODE. That definition doesn't seem very helpful, right? But this means that the input is 0. So you're going to take this ODE that we have up here, right? This guy, this 2y double dot plus 12y dot plus 16y. And if we wanted the homogeneous solution, right, we would set that equal to 0. Right? What does this tell us? This is going to tell us strictly the natural dynamics of this system, right? So we don't have an input on it, right? We don't have any forcing function. This is just how this system behaves naturally. Say like we wind it up and we let it go, and we're not touching it anymore. What's going to happen? Right? I pull the spring. Now I've got a spring and a mass hanging here. I pull it down and I let it go. Right? There's no input on that anymore. What's going to happen? Right? It's an oscillate, right? We have some natural dynamics there. Right? So if we treat this as if the input is 0, we're solving the unforced ODE. Right? So again, we see it here, right? 2y double dot plus 12y dot plus 16y is equal to 0. So we can assume an exponential solution for the homogeneous solution. Right? So we're going to assume that y of h of t is equal to c e to the rt. Why can we assume that? Because we took diffie-q's and we know that that's how this is going to behave. Second order system, we should expect an exponential response, right? So if I have an estimated response for y sub h, I can take the derivative of that, right? And I'll get y dot of h, and y dot sub h is equal to c r e to the rt. And I'll get y double dot. I'll take the derivative again. So now, right now, I've got y of h, I've got y dot, and I've got y double dot, right? And notice I've underlined them on the slides in different colors, and then I've correspondingly underlined the variable that we're going to plug into in our homogeneous ordinary differential equation, right? So we assume a solution form, right? And then we take the derivative twice. Why? Because we have to plug it back in to our unforced ODE, right? We plug it back into our unforced ODE, and that's what this is down here, right? That's what this guy that I'm putting in a box is right here. Or, because everything has a c e to the rt, right, we can algebra the rest of it out. And hey, we're left with 2r squared plus 12r plus 6. C times e to the rt cannot be 0 for all time t. Fact. It can't. Right? So as time increases, c e to the rt cannot just be 0, right? So therefore, in order to make this a true statement, everything inside of my parentheses has to equal 0, right? So far, so good, right? I assume a solution form. I take the as many derivatives of that solution form as I need, throw it into my original equation. And I then algebra to get this one term by itself, right? So when they say bracket term, they mean everything in here, right? So they're saying that since this c e to the RT can't equal 0, right, it will never equal 0, then the only way to make this true is if 2r squared plus 12r plus 16 is equal to 0. Right? That's what we're saying. Now, hopefully, that kind of looks like something that you could solve. But there's a couple ways that you can solve this for 0, right? But what do we get out of that? That's the important thing. So,
Dr. D,
yeah, what's that?
sorry, can you go back? Why isn't there an R above the last bullet point in that expression? An R value.
Where, Dante?
The center of the screen equation, the y sub h of t equals CERT.
Why is there no r there? Because that's the original solution, right? So if I take the derivative of this, right, the r comes down. If I take the derivative of this, the r comes down again.
Okay, gotcha.
Right? So we start with c e to the RT. We just have some standard exponential growth function here times c, right? What is c? C is some constant. How do we determine c? Well, we need initial conditions.
Thank you.
Right, so the part that's in the bracket there, that 2r squared plus 12r plus 16, that's what we call the characteristic equation, okay? The characteristic equation is important because it allows us to get the characteristic roots, right? And so this is a quadratic equation, so we can use the quadratic formula to solve it, or, you can factor it, right? Or, you could take your fancy calculator and solve it in there, right? There's multiple ways that we can do this, right? But the important thing is that we need to be able to get the roots, right? Because the roots are going to tell us a lot, right? And we'll go over what exactly the root responses tell us in the next couple of classes. But if we factor this, what we'll find is we'll get two roots, right? Which we should expect because it's a quadratic equation, right? Second order equation. We get two roots. What are my roots? -2 and -4 in this case. Right, so I can rewrite my characteristic equation as 2 times r plus 2 times quantity r plus 2 times the quantity r plus 4, right? So my roots are -2 and -4. And so my homogeneous solution can be written in terms of my roots. Right, so y of h, the total, the homogeneous solution, y of h of t, y sub h of t, is equal to the contribution, the exponential contribution from both of my roots added together. Right? So I get c1 times e to the -2t plus c2 e to the -4t. Right? So in this case, if we were to take the limit as time approaches infinity, right? So we're going to steady state. What happens? Well, that e to the -2t, right, that e term gets smaller and smaller and smaller and tends to 1, right? Because the exponent tends to 0, right? Because it's negative and it's increasingly negative. It's getting increasingly small. The constants can be determined by the initial conditions, right? In this case, if we use y of 0 is equal to y naught, and y dot of 0 is equal to y dot naught, we can then solve for our initial condition. We can solve for our initial condition. So if we have the characteristic equation, we can understand what the natural dynamics of the system look like based off of the characteristic roots. Right? That's the important thing. So we're going to need to be comfortable with getting the roots of these characteristic equations. Okay. But there's another part to our total solution, right? The other part that we need to talk about is the particular solution, right? Now, if the homogeneous solution is the unforced response of our system, the particular solution is what happens when we apply a forcing function. Okay. It's when our ODE is not equal to 0 on the right-hand side. Particular solution is usually found by guessing a functional form, which is typically related to the input function. For example, if I had a sine wave input, I would expect a sine wave output, right? If I have a step input, I would expect some sort of output related to my step, right? If I have an input force that's a step, I would expect that my output would be related to a step in some way. So if we're driving a linear system by a sine wave sine of 4t, then the force response would also be a sinusoidal function, but with a different amplitude and or phasing, right? Well, again, don't worry so much about the sinusoid stuff for right now. We're going to do a full like 3 to 4 weeks on it. The important part is that you're guessing right here. You're guessing at a solution form based off of what your input is, right? And it should probably be related to your input, right? You would expect that those two things are related. So here is a table that is not in your textbook, but in a different textbook that I then pilfered to give to you. A common differential equation solution. Now notice, these are both in very specific formats. So we've got first order and second order. The first order equation has x dot plus ax equals to b. And the second order, x double dot plus ax dot plus bx equal to c. Right, and in this case, we are told that a cannot equal 0 and b cannot equal 0. So here are our 4 cases, right? First, I have distinct real roots. So if I look at the characteristic equation, I will have distinct real roots, right? So we're in the second order, right? Let's go back up. For first order, right? For first order equations, we're using this. You got a first order system, that's your total solution, right there in the red box, right? B over A plus C e to the negative a t, right? What's B? Well, B is my forcing function, right? What's A? Well, A is the coefficient on X, right? What's C? C is some constant that I need initial conditions to determine, right? And this is my first order solution form. For second order, it depends on what my roots look like, okay? So if I have a second order system that has distinct real roots, right, I will get something that looks like bullet point 1. C1e to the negative, C1e to the S1t plus C2e to the S2t plus C over B, right? And you can pour all of these constants inside of these equations correspond back to the standard form that we have up here. I don't want to call it standard form. So it's going back to the form. Right, so a squared is greater than 4b. Where does that come from? Well, that comes from the quadratic formula. Okay. What if I have repeated roots, right? So I find out that I have 2 roots at 0, 2 roots at 1, right? Repeated real roots give me the equation give me the solution form that I have there in 4.2. Quantity C1 plus TC2 times e to the S1t plus c over v. There's two other things that can happen here. We can have imaginary roots, right? We have imaginary roots. So if we have a system with imaginary roots, then we get something that's a function of sines and cosines. And then finally, we can have complex roots. Well, how are those different? Well, an imaginary root is just on the imaginary axis. Complex roots are complex conjugates, right? And so they exist somewhere in our imaginary real plane, right? So they have an imaginary and a real portion. In this class, we're not going to use I as our imaginary number. We're going to use J. Okay. We'll get into that more so when we start talking about second order systems. These are well documented and well tabulated, right? This is not the only table that exists with standard solution forms for common differential equations. So let's just do that. Let's do it. Let's do differential equations, guys. It's gonna be awesome. Check it out. I got this first order differential equation here. 4y dot plus 8y is equal to 6. And I want the total response, right? So if I want the total response, what does that mean? We're going to do this the long way. We'll do this all the way out. If I want the total response, what does that mean?
You want the natural solution plus the forced solution.
There it is. Exactly, right? So let's start with the homogeneous portion, right? YH of t, right? Okay. So if I'm looking at this, right, before we even get into that, can I come up with my characteristic equation from looking at this? Okay, well, with that. Right, remember, all right, so let's back that up. For a homogeneous solution, right, for my homogeneous solution, we get this, right? 4y dot plus 8y is equal to 0. Okay. Which we can rewrite as this. If we go back, what do we have to do? Well, we're doing this the long way, right? We assume a solution form, right? So y of h of t is going to equal c e to the rt, right? And so I have to take y dot of h t, which is going to be r c e to the rt, right? Then I got to plug these in to my equation. So I'll have 4 times c RCE to the RT plus 2 times CE to the RT is equal to 0, right? I can algebra this, so I'll get 4 times R plus 2 CE to the RT is equal to 0, right? How did you get there? How did you get there, right? Okay, remember, we're going to assume that our solution, our homogeneous solution, takes the form CE to the RT. I need to take the derivative of that, right? Because if I look at my first order equation, I've got this, and I've got this. And I'm going to plug that in. Right? I'm going to plug these in to here and here, right? So this gets plugged in here, this, let's plug in here, which is how we got down to this equation right here, right? I just plug those things in, and I got that. Now it looks gross, right? Now it looks gross. But hey, when I factor out CE to the RT, which I can, because everything has CE to the RT, everything that I'm left with over here is now my characteristic equation, right? Right? That's my characteristic equation. From that, I can determine the roots, right? And because of the way that I've written this out, it should be very clear that what's my roots? What's my root? It's one root, right? It's this first order system. We get one root. What is my root?
-2.
There it is. There it is. I heard it. -2. Well, we know that R is -2, right? Well, that means that Y of H is equal. So Y of H of T, what we originally said was this, right? This was here. I know what R is. This is equal to C, call it C1, e to the -2 T. This is my homogeneous solution, right? So I'm gonna hang on to this. My pen will work. There we go. I'm gonna hang on to this. I'm gonna bring it back later. I'm gonna hold on to it and bring it back later. I'm not gonna evaluate this yet. I'm not gonna evaluate this. Okay. Everybody okay with this? How we got the homogeneous solution? No, the long.
Oh, the long.
No,
Okay,
no, yeah, I said this is.
This is the wrong one.
Let's clear this up. I didn't say that this is the wrong way to do this. I said this is the long way.
That's on you, because I-
No, that's fine. Masks and shields. Masks and shields. And there's a reason why this is the long way. We'll talk about why it's the long way in a second. All right, so that's the homogeneous portion of the solution, right? Now we need the particular portion, right? So for the particular solution, what do we know? Well, we know that f of t, right, is equal to 6. What am I calling f of t? That's my forcing function, right? This is equal to 6, right? I'm just saying that f of t is 6. But that's a constant, right? So this is a constant. So I'm going to assume that my solution form is that of a constant. Right? I'm putting in a constant. I'm going to assume that I get a constant out. Okay? Okay. Well, if I have a proposed solution form, I can also take the derivative of this. And the derivative of a constant with respect to time is 0. Remember, my original equation is this, right? Let's leave this up here so that we can see this guy. And so that's my original equation. So I'm going to do the same thing that I did with the last part, right? I'm going to substitute these things in, right? Remember, this is going to go here. This is going to go here, right? Green to green, red to red. If I plug these things in, I'll get 4 times 0, like that. That's always fun to see. 8 times A is equal to 6, right? Well, hey, I'll take 4 times 0. 8A is equal to 6. A is equal to 6 divided by 8, or as some people might like to call it, 3/4, right? I mean, 6/8 is fun. 3/4 is good too. Some of you who have a proclivity for decimals might want to call it that. That's fine too. Okay, so my total solution has to equal what? Well, it has to equal my homogeneous solution plus my particular solution. Okay, well, the homogeneous solution was C1 e to the negative 2t, right? We came up with that on the previous slide. And the particular solution is just 0.75, or if I offended anybody with my decimals, I apologize. We use fractions, right? 3/4. And that's the thing, right? And we can evaluate this using the initial condition that we were given, right? Remember, we were told that y of 0 was equal to 3. So c e to the back. So this means that we have C1 e to the 0, right? Because time is equal to 0 for my initial condition, y of 0, y t to 0, plus plus 3/4. Well, hey, this becomes 1. So I can solve this, right? 3 minus 3/4 is equal to C1 is equal to 2 1/4, or 2.25. Right? For this one, I will write 2.25. So we can write our total solution here as y of t is equal to 2.25 e to the negative 2t plus 3/4. There it is. I said that this is the long one, right? Why is this the long one? Because hopefully you remember that 2 slides ago, I showed you that really awesome table with the solution forms for things, right? Then we just did this by hand anyway, right? But let's take a look there. That's B over A plus C, right? So, all right, so let's write our equation that way, right? We had 4y dot plus 8y is equal to 6. Well, according to this, I need to divide out by 4, right? Why? Because there's no coefficient in front of the x dot here. Right? So we need y dot plus 2y is equal to 6/4 or 3/2, right? Maybe 3/2. Okay. So that would mean that y of t would be equal to b is 3/2. 3/2 divided by 2. Well, isn't that just 3/4? Plus c e to the negative 2t. If you evaluate that at y of 0 is equal to 3, you'll get 2.25 is e to the negative 2t plus 3/4. So this is the short way. Using the table is the short way. Why can we use the table? Because we know how to do it by hand, right? Just prove it that the table works. Okay. You guys have any questions on this? All right, so there's gonna come a point where you're going to be asked to use a specific method for solving things, and you're going to want to do it not using that specific method. Specifically, once we get to Laplace transforms, and I tell you to use the Laplace transform method to get the system response, and you're like, no, I'm just going to use the table for ODEs, which is great, and we'll get you the right answer, but we'll also get you 0 points because you didn't do what the instructions told you to do, right? So just be on the lookout that when something tells you to use a specific method, you need to use that method, right? And if you're not told what method to use, do it however you like. In the real world, is your boss gonna be like, oh, well, no, I want you to use the Laplace transform method? No, they don't care. But I'm trying to test whether or not you learned the Laplace transform method, so a little bit different. Anyway, that's how we do that part. Right? Ooh, this one looks super fun though too, right? There's so many good ones. So many good ones. So can we solve this one? Sure. Sure we can. Sure we can. So if I have this second order linear ordinary differential equation, and I'm given initial conditions of y of 0 equal to 2 and y dot of 0 equal to -1. Now here's a fun question to ask. If you have a second order system, how many initial conditions do you need to solve that system? Two, right? You need as many initial conditions as you have order of the system in order to effectively solve said system. Okay, so this one, it's second order, right? So this one's gonna probably take us a little bit longer than the last one. And that's true, right? Because why? Well, because you have to take the initial format, right? You have to take the initial, you have to assume a solution form of the homogeneous, right? Then you have to take the derivative twice, plug that in, right? And we can do that, but I think that we've shown that if you do that, what will happen, right? If we do that, what's going to happen? You're going to get this. Right, we're going to get this. You might start noticing, right, between those last two problems, the characteristic equation looks a heck of a lot like the input or the output side of my equation, right? Interesting how that happened. Will it always be like that? Yes. Your characteristic equation will always be here, right? If I'm going to solve for the roots of this system, what do I get? Well, 2r squared plus 8r plus 6 is equal to 0. Well, that's just r squared plus 4r plus 3 equals 0, which is going to give me two roots, one at -1 and one at -3. And how did I get it? Factor quadratic equation or solve it in your calculator. One of those three options. I prefer to do the solving in the calculator. if you have a calculator that does solving, that's gonna be really helpful for you on like homeworks and exams when you're allowed to use a calculator. Right? All right, so those are our roots, right? Well, if we have the roots, what does that mean for us? Well, that means we can get the homogeneous solution as C1 e to the negative 1 times t plus C2 e to the negative 3 times. Remember, our solution form is this c to the R2 business. And we need, each of our roots contributes in some way, right? Each of our roots contributes in some way. The particular solution is where this starts to get long and drawn out. Well, it's not fair to say long and drawn out. It starts to get long, right? But so we're gonna do it all. We're gonna do it all out, and we'll check it against what we have in our table. Okay, we're gonna do it all out. So I've got a particular solution. Look, this is what I'm gonna call f of t in this, right? I have some input that is a sinusoid. It's 10 sine 4t, right? So if I'm talking, whoa, something weird. So let's talk particular solution. Maybe not. It's pen's running out of ink, guys. Pen's running out of ink. Okay, so I'm going to assume a form of my particular solution. Assume a form for my particular solution. All right. I am going to assume that this sine wave can be decomposed or will produce I'm going to assume this solution form, where A and B are the amplitudes. All right, so I'm putting in some sine wave that operates at 4 radians per second of frequency, right? My output will have the same frequency, but it will have a sine component and a cosine component that are added together. Okay. Another way of thinking of this is if you add a sine and a cosine together, it's going to cause your sine wave to shift in some way, right? It's going to cause this shifting of your wave. And so another way of thinking of this, which we will start talking about it much later, is you're going to introduce some phase to this. We're going to introduce some phase. All right, so just like before, I'm going to take the derivative and the second derivative of this. That's all the 4a cosine 4t minus 4b sine 4t, right? Now do it again, negative 16a sine of 4t minus 16b cosine 4t. All right, remember our original equation, 2y double dot plus 8y dot plus 6y is equal to 10 sine 4t. And just marking where they go, in case we forget. We got to plug this in. We're going to plug these particular solutions in to the appropriate y double dot, and y places, right? So this is going to be a very long looking equation. Mm. So we get this equation, right? So all we've done is we've taken our original equation and we plugged in our particular solution for, it, right? To each of the areas. Now, how do we do this? Well, it's not going to be obviously apparent why we do this in this way in the time domain. But when we start talking about the real and imaginary plane, it will be. But we can group all of our cosine terms together and all of our sine terms together in the same way that we do like I and j components when we're talking about vectors. Right? So all of my, wait for it, all of my cosine 4t terms, right? So we got negative 32b, right? That comes from this first. So all of the coefficients, right, of my cosine 4t terms, right? 2 times negative 16b plus 8 times negative 4b, right? Or a, sorry, plus 32a plus 6b is equal to 0, right? Because that final term, my output, doesn't have a cosine term. It just has a sine term, right? And I can do the same thing for sine of 4t here. And I'll get negative 32a minus 32b plus 6a really just doesn't want to work there. That one spot. Is equal to 10. Oh, no, thank you. So that's equal to 10.
Got the y, and then both of the
Where did I get the equation for the particular solution? So if you remember a few slides ago, we said that it would be like a sine of omega t plus phi, right? This is just another way of writing that. Instead of writing that phase angle, we're saying that because we had some sinusoidal input inward or into our system, we're going to get a sine wave that gets shifted on the output, all right? It has to operate at the same frequency as the original one, but there's a little bit extra that shifts it in some ways. Okay. I'm going to take these two equations and I'm going to solve them simultaneously for A and B. And this is what I will get. So then I can write my total solution, right? Because these are this is my, well, so my particular solution in this case is equal to A, right? So this is negative 0.1529 times sine of 4t minus 0.1882 times the cosine of 4t, right? And where did that come from? I just took A and B and I put it back into this equation, right? So my total solution, y of t, is equal to my homogeneous solution, which was C1 e to the negative t plus C2 e to the negative 3t minus 0.1529 sine 4t minus 0.1882 cosine of 4. So what is this telling me, right? This is telling me that I've got some exponential decay that's combined with a sine wave. So I've got this decaying sine wave, right? What it's telling me. That's great, right? That's great. Did I put another stone? I did. Perfect. Okay. So now we've got to solve for C1 and C2, right? So how do we do that? Well, we use our initial condition. Is everybody okay up to this point? Just ring in any bells. We ringing any bells? Hopefully. All right, so let's evaluate this at our initial conditions, right? So remember, we had y total, right? Sometimes I put a little t, subscript t there. Y total was, let me get rid of this thing first. Into right. Y total was C1 e to the negative t plus C2 e to the negative 3t minus 0.1529 sine 4t minus 0.182 cosine 4t. Okay, great. I had initial conditions given to me as y of 0 is equal to 2 and y dot of 0 equal to negative 1. I need a y dot equation, right? Because I have to evaluate this at my initial condition. So I'm going to have to take the time derivative of this equation. And I can get that. And just take the derivative of the equation with respect to time. It's true. This is a tricky one, right? Because it's got sines and cosines and e's. And specific ones that, functions that have specific rules to follow. Right? But if I evaluate these two equations at my initial conditions, y of 0 is equal to C1 e to the 0 plus C2 e to the 0 minus 0.1529 sine of 0 minus 0.1882 cosine of 0 is equal to 2. All right, well, a couple of things happen there for me, right? This goes away, right? Because sine of 0 is 0. This is 1. This is 1. And this is 1. Right? So it's just C1 plus C2 minus 0.1882 is equal to 2. I still need another equation, right? So let's evaluate our y dot equation. Well, that's going to be negative C1, well, e to the 0 is 1. Minus 3C2, well, e to the 0 is 1. Minus 0.6116, cosine of the 0 times 0. My cosine of 0 is 1. And the sine of 0 is 0 still. And this is equal to negative 1. I've got two equations. I've got two unknowns. I'll solve these simultaneously. C1 and C2 then become 3.09 and negative 0.90. So I can rewrite my total solution. Minus 0.9 C to the, that's slowly rolled off the D. e to the minus 32 minus 0.1529 sine 4t minus 0.1882 cosine. And there it is, in all of its glory. All of its glory. Okay. You guys have any questions on that one? Is there a short way to do that one?
Yes.
Yes, this is. You could plug that into your. You could plug it in to. What were my roots? -3 and -1. Oh, that's maybe. Yeah, you can use that table, right? And do it that way. Would it look exactly like what we just got? No. It won't. Because I assume that we've got a sine and cosine function as our particular solution. It won't look exactly the same. We're not going to run through it. We'll keep going. We got it. So, does anybody have any other questions on that? If you wanted to, right? If you really wanted to, right? You could. Really wanted to, you could check your initial conditions, right? You could plug in time is equal to 0 in your equations, right? And see if you return the initial conditions. You should, if you wanted to, but we're not going to run through that. Okay. Right. So let's talk about the complete response. Some of these are like 1 or 2 slides. Okay, so when we talk about the complete response, right, that's different than when you ask for the total response, right? So the total response is the homogeneous plus the particular. The complete response of the system, the way that we're going to define this is our transient response plus the steady state response. What's the difference, right? Well, the transient response is the part of the system that changes as a function of time, and the steady state response is anything that doesn't change as a function of time. Okay? So another way of thinking of this is the transient response is the part of the total response that goes to 0 as the limit of time goes to infinity, right? Or the part that dies out. And the steady state response is the part that remains as time goes to infinity. Here's the thing. This is only true for stable systems, right? An unstable system will never reach steady state because it will exponentially grow and explode. And explosions are typically frowned upon, unless you are in the munitions industry, then they are not. They're smiled upon. Right? So, what about characteristic roots and the transfer function? Is there some connection between the characteristic roots of an equation and the transfer function? You betcha. You betcha. Betcha there is. Right? So far we've seen that the homogeneous and free responses depend on the roots of the characteristic equations. The roots of the characteristic equations can also be determined from our transfer functions. Right? If we look at the denominator of our transfer function and set it equal to 0, we can get the roots of the characteristic equation, because the denominator of our transfer function, also known as the poles of our transfer function, right? The denominator of our transfer function is the characteristic equation. Okay? It is. And if you set that equal to 0 and solve for the roots, you get the poles. So the roots of our transfer function are the poles of our system. So if you're asked to find the poles of a system, right, you're being asked to find the roots of the characteristic equation, right? That's the takeaway. Right, so find the roots. Right, so we got to find the roots. Okay, I've got an equation there. I need to determine the characteristic equation of the roots, and I need to determine the transfer function, poles, and zeros. All right, we didn't talk about what zeros were, right? Zeros are if we have roots of the numerator of our transfer function. For this class, poles and zeros don't really mean anything. They're more of a controls thing. Right? We're not going to really talk about that. But what's important to know is that the poles are the roots of the characteristic equation, right? So I want the characteristic equation and the roots, right? Well, remember, if I want the characteristic equation from this, I can easily get it. Right? It's this. This is my characteristic equation. Where did he get that from? Remember, he said that if you look at, you don't need to solve the homogeneous solution to get the characteristic equation. If you have a second order differential equation, the characteristic equation is given to you by looking at the actual equation, right? We're going to get 0.04 r squared plus 16, right? And we set that equal to 0, right? We set that equal to 0. Why? Because we want to solve for the roots. We want to solve, oh, there it is, for the roots. What do I get if I solve for the roots here? Well, this is going to be interesting and fun. This is the first time that we've seen this, right? So if you do the quadratic equation here, you'll get, not 36, we've got a complex conjugate root here. It's got a real and an imaginary portion. That's gross, right? Yeah. How do I do this? Well, you use the quadratic equation, you solve it. Or, pro tip, if you have a fancy calculator, like a TI-89, I know does it for sure, you can use the command csolve for complex solve. And csolve will punch out imaginary roots for you. Okay. So I got the roots. Great. Part A done, right? That's right. I needed the characteristic equation and the roots. We're good. Right? What's the transfer function, poles, and zeros? Well, I didn't get the transfer function, but I know the poles already, right? Because I just told you that the poles are the roots of the characteristic equation. But if you didn't believe me, and we wanted to do the transfer function anyway, right? I'll do my D operator business here. Right. Do my okay, forgot my times y is equal to f of t, right? And then y of t over f of t is equal to 1 over 0.04 b squared plus 16 b plus 7. Awesome. Hey, look, this and this look exactly the same. You solve that, find where d is equal to 0, right? You got the roots of the characteristic equation again. We don't have any zeros here, right? Why? Well, we didn't talk about it, but zeros only happen if we have something that looks maybe like this in the numerator, right? I know that we had like an s plus 2, or sorry, in our case right now, we had something like a d plus 2 in the numerator. Then we would have a 0. We don't have any roots. Right? We don't have any roots in the numerator. We don't have any zeros. We'll talk a little bit more about poles and zeros when we get to Laplace transforms and what they specifically mean. We're not going to go overly into it, right? The reason being that it's more of a controls concept, and we're not really going to use them for anything in this class. All right. Any questions on characteristic roots? Right, remember, the characteristic roots tell us something about the unforced dynamics of our system, right? They're important. They help define our
Dr.
system.
D,
Yeah, what's up?
are you talking? I think I might have lost audio.
I am talking.
I can still hear you.
Okay, other people can hear me. If you can hear me, throw a thumbs up. I'm looking at the computer. If you can't hear me, put the party favor thing. I didn't catch anybody with that one. Probably. All right. Cool.
Hello, can you hear me, Dr. D?
Okay. Audio issue, Dante. That's, I don't know what's going on. All right. So if you have any questions about characteristic roots and the transfer function and how they're related, right? We can talk about DC gain and steady state. Okay. DC gain and steady state. Now these are important ideas, right? Because these are things that we can tell about our system. If we have our model, right, we should be able to tell what the DC gain and what my steady state look like, right? So DC gain is an extremely useful analysis technique where we can compute the steady state response of the system to a constant input. All right, so it's derived from circuit analysis, right, because it implies that there's some constant, right? DC means that there's some constant, not oscillating input. So by definition, the system's DC gain is the steady state gain to a constant input. So if we had something like a step, right? Something that is just on, right? for the case when the output is a constant value at steady state. DC gain for a given transfer function is computed by simply setting S, or in our case, remember, we've been using G so far, right? We set S of D equal to 0, and the results arise from the application of the final value theorem in Laplace transform theory, which we haven't talked about yet. So, what we will. Right, and then there's a note at the bottom that S equal to 0 is similar to setting D equal to 0, right? Think of it this way. At steady state, right? If you're at steady state, what part of your system is changing with respect to time? At steady state, is your system changing with respect to time?
Only in 0th order.
Well, let's just go with like a yes or no for this one. Let's not go with the it depends on this one. Yes or no? You are at steady state. Will you change with time?
No.
No, right? The idea, the premise is that you are steady. And if you're not changing with respect to time, doesn't that mean that your time derivative is equal to 0?
Yes.
So that's why we're setting D equal to 0 when we're looking at DC gain, because D is equal to ddt is equal to 0 when there's no change with respect to time. Okay, so let's try one here. And I've got this block diagram here, right? Because block diagrams are the new hotness that everybody loves, so we're going to use them, right? And look, I've got this input voltage. It's 2 volts. It goes into some solenoid, right? That block diagram. That gives me my solenoid dynamics. It outputs an electromagnetic force, which goes into my spool valve, right? And that comes out as some valve position in meters. Okay. So what is the DC gain of the solenoid, right? What's the DC gain of the first transfer function, right? Well, let's rewrite it as our time domain transfer function. When I want the DC gain of this transfer function. How do I find it? What did I say on the last slide? What do we do for DC gain? Set what equal to 0? Yes. The pen. We set our pen equal to 0. She said D. We'll go with that. So if I set my D equal to 0 in this, and I set my pen equal to 0, then nobody can see. I get 12 over 1.5, right? 0.003 times 0 gives me 0. So I just get this, right? And then this, if you did it out, turns into S, right? Yeah, I have an extra 0. It should be 0.0. It doesn't matter. It's 0. Apparently, that turns to S because the screen won't let me write anything there. But it should be 8. That should equal 8. Right? 12 over 1.5. I know it doesn't equal S, guys. There we go. It equals 8. All right. Awesome, right? So what is this telling us? This is telling us that at steady state, our transfer function turns into a gain block, right? It just turns into an amplification. Right? At steady state, we're just amplifying our input signal, okay? Right, so if we were to draw this at steady state, you'd have some En times a gain of 8, gives me some output, goes into another gain block, right? So instead of having the transfer function there, I just want a gain. So what's the DC gain of my spool valve? What's my DC gain here?
Is it
Would it
one?
just be 1/7,000?
Would be 1/7,000. Exactly. Which is a giant gain, right? 1.43 times 10 to the minus 4. Obviously, without having to use a calculator or write it down in my notes. So at steady state, right? This is my block diagram now at steady state. At steady state, these things turn into gain blocks, right? Because the transients have died out and we're left with something. Okay? So at steady state, right, if we know that our input voltage, which we were told was 2 volts, I can figure out my steady state electromagnetic force. How would I figure that out? Well, look at the gain. Look at the state. Look at the block diagram for steady state and tell me what the electromagnetic force is for this system at steady state.
AEN.
Say that one more time.
8 times EN.
Right, 8 times E in, right? And we know that E in is 2. So 16 newtons. What about my steady state spool valve position? You're looking at the block diagram. How do I find my spool valve position? The Y. I'm looking for Y. What's Y? You don't have to give me a number. Just tell me how you get it.
One over 7,000 times the electromagnetic force.
Yes, exactly. Exactly. Right, so that's 16 over 7,000. 16 times 1 over 7,000, which we can all do in our head, obviously, which is 0.0029 meters, right? Or 2.3 millimeters. What if you were asked to find the DC gain for the entire system? How would you find the DC gain for the entire system? That's a fancy way of me asking you to collapse this block diagram into a single transfer function. If I wanted to make a single transfer function here, how would I do it?
Multiply the 2 blocks.
Multiply the 2 blocks. If I wanted the DC gain for the entire system, right? Looking at the steady state block diagram, what is the DC gain for the entire system?
8 over 7,000.
It is 8 over 7,000. And guess what? If you multiply 2 times 8 over 7,000, what do you get? 16 over 7,000, which is going to give you 0.0029 meters. Right? The idea of DC gain is powerful because if we know we have a constant input, then we can make assertions about the response of our system at steady state immediately, given a model, right? Specifically given the transfer function. Given the transfer. This all stems from Laplace transform theory, which we haven't gone over yet, but we will in a couple of weeks.
Dr. D,
Yeah,
you have 2.3 millimeters, but 0.0029 meters. Is it supposed to be 2.9 millimeters or?
Yeah, yeah, yeah. 2.9. It's totally depends, guys. It's totally depends. Hold on. One of those is wrong. Let's go back to the notes. Should be 2.3, not 2.3. It says 0.000229. My notes are for the other national firm. Apologize. Should be 2.3. Okay. You guys have any questions on the idea of DC gain? This is something that's going to be really useful for us when we get towards frequency response, or if you want to know what the steady state response of the system is very quickly. Right? Okay. Let's talk about first order systems. First order systems, I'd like you to recall that many of the models that we've derived so far in this class have turned into first order system models, right? When we're talking about circuits, we always had a series of first order differential equations that we were talking about, right? When we talk about fluid and thermal systems, we tend to keep those in terms of first order systems, right? So there are real life systems that can be discussed as first order, right? Including mass damper mechanical systems, RL or RC circuits, single chamber hydraulic systems, single vessel pneumatic systems, or single capacitance thermal systems, right? Like these. And if we did these models out, right? We did these models out, we would get equations that look like this. Right, so first order mechanical rotational system with no spring. First order RC electrical circuit. A first order pneumatic chamber with a laminar valve flow. A first order thermal chamber. These are all examples of common first order systems. Turns out that we can talk about first order systems by discussing them in a standard form. Why do we want to use the standard form? Well, there are things that we can pull directly off of our, there are things that we can pull directly off of our model if we have it in standard form. Right? And all of the previous models that we just looked at on the prior slide can be written as the standard form that I have at the top of this slide. Tau y dot plus y is equal to A times u of t. Tau is a constant. Right? Tau is a constant. The dynamic variable is y. And it's defined, we can define these as all of our, in this table, right? So if you're looking at our mechanical rotor, our rotational mechanical system, our dynamic variable was omega, and our constant tau was J over B. In all of the other examples, it's RC, R times C. That constant A there, The constant A is unity for all of our models except for the mechanical system where it would be 1 over B. Okay? So let's go back and look at these models again and we'll talk about it, right? So what is this, right? So if this is, we're putting this into the standard form, tau omega dot plus omega is equal to A times T, right? Well, in order to get this in this form, I have to divide everything by B, right? In order to get that in this. So what we're trying to do, the rest of them, notice my dynamic variable is already clear, right? When he says clear, what does he mean? The form here is that you want y to have a coefficient of 1. You're going to clear the coefficients from the front of y in the standard form. And that's how you get tau, and that's how you get A. Right? Everybody okay so far? I haven't made it clear as to why you want to have things in standard form yet. But we're getting there. It has to do with tau. Now, when you guys hear tau, what do you guys think of? What has tau been used for in other classes that you've taken thus far? Think about that. What could tau be? So let's talk about the natural response of the first order system. When we're talking about the natural response, we're talking about the homogeneous solution, right? So that means that our equation is equal to 0. So we've got tau y dot plus y is equal to 0, right? And we can get our one root characteristic equation, right? Which is r plus 1. So in this case, our characteristic root is -1 over tau. So we can rewrite the homogeneous solution as C is equal to YH of T is equal to C e to the -t over tau. -t over tau. Just as a note for the case, with no input, the constant C is simply the initial condition, so it's going to be Y naught. Y. Okay. Interesting. And this is right here, right? This Y equation. C e to the -t over tau. That's going to be important, right? That's a big deal, he says. And it is. It's a big deal. It's going to be a big idea. Because -1 over tau is important. Because tau is important. So, just to have it here on the slide, right? This is just the natural response with no input, right? With an initial condition of Y naught. Y of 0 is equal to something. Well, call it Y naught. The constant tau has to have units of time so that the exponent is non-dimensional. And we call this the time constant. Hopefully we've heard about time constant before in either differential equations or circuits or somewhere, right? Time constant plays a big role. What is time constant? What is it? Great question. The first order natural response has the following characteristics. 1, exponential rise or decay to a 0 steady state value. Right, so we're either going to exponentially rise to a steady state value or exponentially decay to a steady state value. That means what? That means that we have some measure of stability in these first order systems that's already inherent. When T is equal to tau, the natural response will have decayed by 36.8% of the initial value. Okay. So e to the -1 is 0.368, right? So when we've gone one time constant, our transient response has decayed by 37%. When we reach 4 time constants, when we reach t is equal to 4 tau, we consider the natural response to have died out. We consider it to be at steady state at 4 tau. Because e to the -4 is 0.02, which is pretty small, 2% of the initial value, right? Beyond that, if you were to go to another time constant, you don't get significant decay at this point anymore. So we consider 4 tau to be the point at which we hit steady state. And so anything beyond 4 tau we consider to be steady state. Settling time is 4 tau, right? That's the idea of settling time. Right? If you needed to calculate the settling time of your system, you need to know 4 times the time. Right? 4 times the time. I want you to notice something else here. I'm going to go back to this. The characteristic root of our equation is 1 over the time constant, right? Characteristic root of our equation is 1 over the time constant. So you don't even need to write out the full solution to know what the time constant is for a first order system, right? You can look at the roots. And if you take 1 over the root, you'll have the time constant, right? 1 over the root is the time constant. Well, time constants, the thing that we need when we're talking about first order systems. Time constant is basically everything for first order systems. If we know the time constant, we can draw the response of that system. That's right. We know the time constant. We need it where? So there's a couple things. We need the time constant and we need the DC gain. Then you can characterize a first order system, right? So let's. You guys have any questions on first order systems? All we've talked about is the natural part, right? So there's a second part of this response that we haven't talked about yet. And the second part of this response is the forced part, right? We have the natural part, we need the forced part. So how do we talk about that? Well, we're going to use a step response in particular. So once again, we have our standard form, right? But this time it's not equal to 0, it's equal to a times u of t. And suppose that we're going to use a unit step, right? Or just a step input u, right? There's some constant. Well, that, remember, step input gives me a constant input, which means that we can probably use DC gain for this. Right? We probably use DC gain for this. So we already know the natural response, right? If we're looking at the total response, we have y sub h, right? We just calculated y sub h on the previous. We know it's an exponential function. The forced response is a constant input, so we should expect to get a constant output. At steady state, right, if I take my equation and I evaluate this at steady state where u of t is equal to my step function, right? At steady state, the time derivative goes to 0, right? Because it's steady. Nothing is changing with time. So I'm left with y is equal to a times u And so my particular solution is my steady state solution. It's just the coefficient A times the final value of my step. Everybody cool so far? So the question is, why did U of T become capital U, right? Because we're going to assume that we're using a step input, right? It's okay. So we're assuming that step input. Remember, last class we went over the step input. It's that we use capital U to talk about it. It's that piecewise function that is 0 at all points except for once it turns on, it instantly becomes whatever the value is that we associate with it. Okay? Any other questions? Nope, nothing. So we can put these two things together, right? Because we want the total response. So we know the natural portion is an exponential. We know the final or the steady state portion is the particular solution. We can add the two together. And if we evaluate this at our initial conditions, where y of 0 is equal to y naught, right? Then y of 0, right? We can figure out what c is here, right? C is going to be y naught minus y steady state. So we can rewrite our total solution right here. I'll put a red box around it because this seems like it should be important. And then I'm going to put a blue box around the red box. Right. I'm not going to use green too. That seems excessive. So what do we get, right? Based on everything that we've done, we get a total response, a complete response that has this transient portion, which is a function of time, and then this steady state portion that is not a function of time, that is just a constant, right? If you took the limit as time went to infinity of this equation, what would happen? The transient response would go away because we would eventually get E approaching negative infinity, right? We get smaller and smaller and smaller and smaller and smaller and smaller. So it's almost 0. That's fine. And you're left with Y steady state, which I think makes sense, right? You put a step input of 2 volts into your RC circuit, right? You're going to get a step, you're going to get a constant voltage out of that circuit, right? Depends on your resistance and your capacity, but you'll get something. Okay. Does anybody have any questions on this? I know there's no numbers, right? No numbers, so I know. Does anybody have any questions? Oh, I went the wrong one, sorry. All right, so what we need to talk about now is how do we sketch the response, the step response of a first order system by hand. We want to talk about how we do this by hand. Because the most important part about being an engineer is your skills as an artist. This is what they don't tell you. Right? I mean, you guys have seen, I don't mean to brag, but you guys have seen me draw, right? And so, you know, this is a serious business. But anyway, Dr. D, why do we need to learn how to do this by hand when we have things like MATLAB to do this for us? Because think of a world, just imagine for 1 second, that you don't have access to a MATLAB or a computer program at all. Say you're about to get on a international flight for business purposes, and you don't have a charger, and you're sitting in a row that doesn't have, right, that won't let you charge, or your computer's just dead, right? And you need to get some work done because reasons, right? If you can get a quick sketch of what the system response should look like, reasonably accurate, then you can test it with your MATLAB or Simulink later, and you should be good to go, right? So how do we do this? Well, the first step for doing this is we're going to rewrite our model in the standard form, and we're going to find the time constant, right? Once we have the time constant, then we need to find the settling time. Remember, that's just 4 time constants. Then we need to find the steady state response, because once I told you guys a few minutes ago, if you have the time constant and you have the steady state response, you can draw this pretty easily. Then we're going to sketch an exponential response from the initial condition, right? So from our starting point to our steady state value. If the response reaches steady state at 4 tau, right? And the total response will decay down if y naught is greater than steady state, but it will grow upward if it is less than steady state. These are the general rules, right? If you follow these steps for drawing a first order response, it should be good. Should be good. Let's try one. So, this is probably where we'll call it. So I've got this first order differential equation. I want to determine and draw the response. All right, so first things first, put this in the standard form. Some of you may have noticed that this is the same equation that we had a few slides ago from our solenoid dynamics, right? Some of you, maybe nobody. But I got to put this in standard form, right? So what's standard form for first order? Nope. Plus y is equal to a times u of 2. Okay. So we need to put this in this. So we need to divide everything by 1.5. Right? So I'll end up with 0.002 f dot plus f is equal to 8 times En of. Well, what were the things? Sorry, so if we're going to follow this step by step, right? Rewrite the first order model in the standard form. Check. Estimate the settling time as 4 time constants. All right, that's part 2. Well, I'll be. You mean that if I write it in the standard form, it gives me usable information right away that I can automatically use to calculate the time constant and the settling time? Yes, 100%. Settling time is equal to 4 times tau, equal to 4 times 0.002, 0.008. That's a pretty fast settling time, right? That's less than 1/100 of a second for the system to reach steady state. Pretty fast. I mean, I guess if you enter that, yeah, it's pretty fast. 8 milliseconds. I mean, if you're a high-level gamer, like PvP gamer, I mean, that's pretty slow. You need to be faster than that. You can't even react that fast over PvP. All right, anyway, so we've got the settling time, right? So the last part is we need the steady state response, right? So we're looking at our equation again, right? 0.002 F dot plus F is equal to 8 En of T. Now, something that wasn't written here, but remember from our diagram before, we know that En is a step input of 2 volts, right? Remember that? Remember that? Which means that at steady state, we would know that this is going to hit 2 volts as our input, right? So at steady state, if I'm looking at this equation, remember, the transient part, the derivative goes away. So F at steady state is equal to 8 times En at steady state, which we know is 2, which gives us 16. And that's in newtons. Okay, so did I do the steps? Let's see. We rewrote the equation as a first order model in standard form. Yep. We estimated our settling time. We computed the steady state response for a constant input. That's a little like DC gain. It is. Now we need to sketch an exponential response from the initial condition to steady state. Well, the initial condition isn't given. So we just stop, right? No. Just assume that it's 0. Start at 0. Imagine for a second, if you will, a world where you started with no current or no voltage, and then you turned on the switch, and then you got some voltage. Imagine that for a moment. All right, so we can draw this now, right? How do we draw this? Well, I have a graph. I'm going to put my time in milliseconds on the x-axis. I'm going to put my force in newtons on the y. I'm going to say that this is 16, and then I'm going to go down by 2s and hope that I do this to scale. Hey, that's not bad. I'll take it. Okay. Well, what do we know? First of all, I know that this is my settling time. So I'll draw a line up. Right? This is tau. I also know that this red line is my steady state, right? That's F steady state. So I can say that anything beyond this point is going to be considered to be this straight line, right? Because I start steady state at 4 tau. Is that 100% true and accurate? It's an approximation. It's going to be close enough. You're going to be within 2%, right? A steady state at that point. What do we draw now? Well, we need an exponential curve that goes from one to the other. And that's not the greatest, but it'll do. How about that? That's better. I'll take that one. This is the system response to a step input. Let me get rid of that box there. You can check this using MATLAB, and you know what? It'll be pretty darn close. It'll be pretty darn close. Not going to be exact, right? Drawing an exponential by hand isn't going to be exact. But it's not the point. The point is not to be exact. The point is to get in the ballpark so you understand what the system response looks like, so that when you do your analysis, you understand what you're supposed to be getting out, right? That's the point. You guys have any questions? We don't have time to do pulse response today, so we'll do that next class. Okay? Do pulse response next class, and then we'll get into second order systems, and we'll spend the rest of the week talking about how we can do things with second order systems. Okay. You guys have any questions? Anything? Well, if that's the case, I did promise you that we would tie up our story based off of the quiz score there. So here we go, right? Remember, we left off, you had to tell Professor Q everything that the old homeless lady had told you, right? So you start telling Professor Q about your day, you tell him everything the crone told you. You make a special point of specifically mentioning the part where the crone called you the instrument of my vengeance. Then, when I was walking away, she yelled, 3 witches you shall meet upon the road to your fate. The first is twilight, the second is night, and the third is the coming day. Is that everything? Yes. Yes, he responded. Well, that was a pretty crazy morning you had. Unfortunately, I can't let you leave now. I've waited too long to enact my plans to let you ruin them. Oh, that's not correct. Go back to the story, man. You see, if the crone has warned you about me, then the mother cannot be far behind. Professor Q pulled out a staff from his closet. He pointed it at you, and it started to glow. Get in the closet and give me your phone. Don't make this harder than it has to be. You got in the closet, too stunned for words. You heard the door lock, then the office door locked as well. It was dark. Man, I really wish I had showered after the crone touched me, he thought. Will be continued in exam 2, the mother.
It sounded really wrong.
Oh, no. You got locked in the closet. All right. And so, because it is Thursday, here we go. This is the question for today. If we all know that the moon isn't made of cheese, but if it were made of spare ribs, would you eat it? Yes, no, or how are they cooked?
You believe in the moon?
I do believe in the moon, yes.
Interesting.
Yeah. I have some interesting YouTube videos planned. Dr. Staggs and I will get to the bottom of whether or not the moon exists. Some very interesting content planned for it.
That's like asking if birds exist.
Birds are government spies. They're robots.
No, they're not.
Yeah, they are. Everyone knows.
Even as geese cannot be robots.
You just used the perfect example.
100%
Birds don't
robots.
exist. Thank you.
I mean, if they were robots, that's exactly what they would say, though, right? So.
Again, something as evil as geese cannot be robots.
Okay. Looks like, yeah, you guys would eat it. Maybe you should just grab some breakfast or something before class. So that weird space ribs might not be the best thing for you. Just the same. Yeah. Throw into this one. Right. Again, if you're going towards the bottom half, coming off the hours tomorrow from 3 to 5, Monday from 9 to 11, every day except Thursday and Monday from 3 to 5 p.m. I'll be there. Be there. Apologize, but I have to teach independent study for 2.5 hours after my next class.
So, just to clarify for my the lab is called
Rotational electromechanical system.
Okay, so that's the same. Lab is independent,
Right.
So I want you to
There's a second one that should be on it. If it's not, let me know. I'll make sure it's there.
okay.
But there should be a second one that should be episode 2 of the labs thing for rotational electromechanical system.
Now, let me almost right now.
Sure. Oh man, because I put the wrong one in here, guys. That's why. That's why I told 30. Good catch. Uh-oh. Well, that's going to be a problem for later. I'll deal with it later instead of right now.
Yeah, okay, so it says, yeah, lab rotational electron.
picture of that so that, I don't do it after that. My bad, guys, my bad. Uh-uh.
Okay, we know you like them better.
It's not true. Like
It's
everybody,
good. I don't know if you kids from these whole parents can talk
well, that seems rude. This is weird. Telling me that I'm not in the meeting, that I'm in the meeting.
And
Okay.
that lab, is it done with same partners? The different partners?
You can do it, it's gonna be partners, you can do it in groups of 2 or 3 again. But you need to,
I know it said submit your individual.
yeah, it's gonna be the same deal as last time, just,
Okay.
the same deal as last time.